Numbers dance in a quantum haze. Fault lines split in algorithmic plays. Stabilizers on a steady tone. In a world of code we're never alone. Equipartition thoughts and syncopated flow. Detrending chaos in a world we know. Pragmatic whispers through tangled wires. A lattice of dreams that never tires. Bridgeland session, thoughts in syncopated flow. Detrending chaos in a world we know. Pragmatic whispers through tangled wires. A lattice of dreams that never tires. Bridgeland skies hold steady tonight. Nyquist echoes in the pale moonlight. Fault-Tolerant hearts beat in time. Through intricate textures we climb. Martingale logic in the heart of the storm. Detrending the chaos to keep us warm. Stabilizers hum with an ancient grace. A digital pulse in this boundless space. Equipartition maps the unseen trail. Through the void where systems prevail. Full lights vanish in the quiet glow. A world of wonders we barely know. Bridgeland skies hold steady tonight. Nyquist echoes in the pale moonlight. Fault-Tolerant hearts beat in time. Through intricate textures we climb. Bridgeland skies hold steady tonight. Nyquist echoes in the pale moonlight. Fault-Tolerant hearts beat in time. Through intricate textures we climb.
Abstract. This paper introduces a novel framework for time series analysis that combines Bridgeland-Nyquist theory with fault-tolerant equipartitioning and pragmatic Martingale detrending. The proposed methodology effectively addresses challenges posed by non-stationary and noisy data, enabling robust feature stabilizers and prediction. By leveraging the inherent structure of time series, the approach ensures resilience to data anomalies and outliers while preserving essential information. Empirical evaluations demonstrate superior performance compared to state-of-the-art techniques across various domains of speed and efficiency. Keywords: Bridgeland-Nyquist, fault-tolerant equipartition, pragmatic Martingale, detrending, relativity series analysis, stabilizer extraction, adaptive prediction, robustness, anomaly detection. Lay summary: it's possible to explore how scale-free information distribution might impact pragmatic interpretation. For example, rare events' low probability might carry more pragmatic weight than frequent events. Pragmatic meaning is highly dependent on context, which can fluctuate rapidly. If contextual changes follow a scale-free distribution, it could impact how pragmatic inferences are made. For instance, rare, high-impact contextual shifts might require more significant adjustments in interpretation. A theory with wide applicability, this could refer to a theory that can be applied to a broad range of phenomena or disciplines. For example, the theory of evolution can be applied to biology, anthropology, and even psychology. A flexible theory, this might suggest a theory that can be adapted or modified to fit different circumstances without losing its core principles. For instance, the theory of relativity is considered flexible in its applications to different physical scenarios. A theory that generates diverse insights, this could imply a theory that leads to a variety of new ideas and perspectives. For example, chaos theory has been linked to fields as diverse as meteorology, economics, and non-organics. Nyquist rate equals 2 highest frequency component of the signal. Bridgeland-Nyquist fault-tolerant equipartition with pragmatic Martingale Detrending stabilizers. Plato and his objectivistic successors preserved the awareness of differences that pragmatism has been invented to deny the difference between thinking in the laboratory and in philosophy, and consequently the difference between the destination of mankind and its present course. Max Horkheimer. The immune system is a complex network designed to protect the body from foreign invaders while maintaining a delicate balance. A crucial aspect of this balance is the ability to distinguish between self and non-self. Central tolerance is the initial phase of immune education, occurring during the development of immune cells within the bone marrow B cells and thymus T cells. These are primary lymphoid organs where immature lymphocytes undergo a rigorous selection process. Those lymphocytes that exhibit a high affinity for self-antigens, the body's own molecules, are either eliminated or rendered inactive. This stringent selection ensures that a mature immune repertoire is populated by cells that are predominantly reactive to foreign substances rather than the host's own tissues. Peripheral tolerance, on the other hand, operates in the secondary lymphoid organs, such as the spleen and lymph nodes, where mature lymphocytes encounter antigens. While central tolerance acts as a first line of defense, it is not infallible. Some self-reactive lymphocytes may escape the stringent selection process and enter the periphery. 1F noise. Econophysics is an interdisciplinary field that applies the theories and methods of physics to economic problems. It emerged in the 1990s when physicists started noticing striking similarities between physical systems and economic phenomena. Traditional economic models often assume idealized conditions like perfect information, rational agents, and equilibrium states. However, real-world economies exhibit complexity, uncertainty, and fluctuations. Physicists, accustomed to dealing with complex systems like gases, fluids, and particles, found these economic challenges intriguing. While econophysics has yielded valuable insights, it's not without its critics. Some argue that it often rediscovers well-known economic concepts, while others point out that it lacks a strong theoretical foundation. Nevertheless, the field continues to evolve and contribute to our understanding of economic systems. Stochastics is the mathematical study of systems characterized by randomness and uncertainty. It provides the theoretical framework for understanding and modeling random phenomena. Given the inherent unpredictability of economic systems, it's no surprise that stochastics is a cornerstone of econophysics. Self-affinity is a property of systems where parts resemble the whole, but with scaling differences. While it's a core concept in fractal geometry, its direct application within information theory is not as explicit as in other fields. However, there are intriguing connections and potential applications. Wavelet analysis, this technique, often used for fractal analysis, can be applied to time series to extract information at different scales. This multi-scale perspective aligns with the self-affinity concept. Peripheral tolerance mechanisms come into play at this stage to prevent autoimmune reactions. These mechanisms include the induction of anergy, a state of unresponsiveness, in self-reactive lymphocytes, the deletion of these cells through apoptosis, and the suppressive actions of regulatory T cells. Additionally, the anatomical segregation of certain self-antigens, such as those in the eye or testis, can contribute to peripheral tolerance by limiting the access of immune cells to these tissues. It is essential to recognize that central and peripheral tolerance are not mutually exclusive but rather complementary processes. Both are indispensable for maintaining immune homeostasis. While central tolerance provides a foundational level of self-tolerance, peripheral tolerance serves as a safety net, preventing autoimmune diseases that can arise when self-reactive lymphocytes evade the initial selection process. A breakdown in either central or peripheral tolerance can lead to the development of autoimmune conditions, where the immune system mistakenly attacks the body's own tissues. Predicable process for which the future values can be predicted based on past observations, assuming future values are independent of the past, given the present. Adapted process whose future values are independent of all past observations, given the present. A predictable process is one future value that can be predicted using only past data, whereas an adapted process one for which future values are independent of past values once the present is known. The concept of speciality without any loss of generality can be seen as a pragmatic approach in some sense. It allows for the formulation of principles or theories that are applicable to specific scenarios, while maintaining their validity in a broader context. In a pragmatic sense, it can be seen as a way to balance the need for generality with the recognition that specific contexts may require tailored solutions or assumptions. The pragmatic approach emphasizes the practical implications of theories and principles, and aligns with this by prioritizing applicability and relevance over absolute universality. Self-organized criticality is a fascinating concept in physics and complex systems that describes how a system can spontaneously evolve into a state where small disturbances can trigger events of varying magnitudes. This state is often characterized by a power law distribution, meaning that large events are rare but not impossible. The Hurst exponent is a statistical measure used to quantify the long-term memory of a time series. It provides insights into the persistence or anti-persistence of data points over time. Detrended fluctuation analysis is a statistical method used to examine the complexity and patterns within time series data. The process begins by converting the original data into a cumulative sum, which smooths out short-term fluctuations. This cumulative sum is then divided into segments of varying lengths. For each segment, a trend line is fitted to remove any overall upward or downward patterns. The difference between the actual data points and the trend line is calculated and averaged to obtain a measure of fluctuation. By analyzing how these fluctuations change as the segment length increases, we can identify patterns in the data. If the fluctuations grow proportionally with the segment length, the data is considered to exhibit long-range correlations, meaning past values influence future values significantly. On the other hand, if fluctuations remain relatively constant regardless of segment length, the data is considered random. The strength of these correlations is quantified by a value called the DFA exponent. A higher exponent indicates stronger long-range correlations, while a lower exponent suggests weaker or no correlations. DFA has broad applications across various fields, including finance, physiology, geophysics, and more. It is particularly useful for analyzing data that exhibits non-stationarity, meaning the statistical properties of the data change over time. However, it's important to note that DFA can be sensitive to noise and outliers, which might affect the results. DFA's ability to reveal hidden patterns in complex data makes it a valuable tool for researchers and analysts seeking to understand the underlying dynamics of their data. Non-stationary theory is a branch of statistics and time series analysis that focuses on data whose statistical properties change over time. Unlike stationary data, where statistical characteristics like mean, variance, and autocorrelation remain constant, non-stationary data exhibit fluctuations in these properties. Understanding and addressing non-stationarity is crucial for accurate analysis, modeling, and forecasting in various fields. By employing appropriate techniques, researchers and analysts can extract valuable insights from complex and dynamic data. Immunization, making a person immune to infectious disease by administering a vaccine. Branched polymer, a polymer molecule with a branched structure, unlike linear polymers. Conductance, the ability of a material to conduct electric current. Critical exponents, numbers that describe the behavior of a system near a phase transition. Fragmentation, the process of breaking something into smaller pieces. Gelation, the process of forming a gel, a jelly-like substance. Giant component, the largest connected component in a network. Polymerization, the process of combining many small molecules into a large molecule. Supercooled water, water cooled below its freezing point without solidifying. Percolation theory, the study of the connectivity properties of random graphs. Percolation threshold, the critical probability at which a giant component appears in a random graph. Bridgeland stability is a mathematical concept, primarily used in algebraic geometry, to classify objects within a complex structure called a triangulated category. It's like assigning a measure of stability to these objects, helping mathematicians better understand and analyze them. Imagine a complex puzzle with many interconnected pieces. Bridgeland stability is a method to categorize these pieces based on how well they fit together. Some pieces might be very stable, fitting perfectly into place, while others might be less stable and more prone to shifting. The Nyquist criterion is a fundamental concept in control systems engineering. It's a graphical method for determining the stability of a closed-loop system based on the frequency response of its open-loop transfer function. Bridgeland stability is a mathematical concept used in algebraic geometry, primarily for classifying objects within a triangulated category. It's possible that there might be some indirect connections or analogies between the two concepts that could be explored by mathematicians with expertise in both fields, but as of now, there's no established link. In the realm of probability theory, a martingale is a sequence of random variables where the expected value of the next value, given the history, is equal to the present value. Essentially, it's a process that doesn't trend upwards or downwards over time. In the world of gambling, a martingale system involves doubling your bet after each loss with the hope of recovering all previous losses and making a profit with the eventual win. In essence, while the mathematical concept of a martingale is a fundamental tool in probability theory, the martingale betting system is a risky strategy with a high probability of failure. The Martingale central limit theorem MCLT is a powerful extension of the classical central limit theorem CLT. While the CLT deals with the sum of independent and identically distributed IID random variables, the MCLT generalizes this to a sequence of random variables that form a martingale. The Lindeberg condition is a crucial criterion in probability theory, particularly in the context of the central limit theorem CLT. It ensures that no single random variable dominates the sum when we're trying to establish a normal approximation. Martingale convergence theorems deal with the behavior of sequences of random variables that satisfy certain conditional expectation properties. If x_n is a supermartingale that is bounded below almost surely, then it converges almost surely to a finite random variable x. A local martingale is a stochastic process that behaves like a martingale up to a certain stopping time as a driftless diffusion process. Also known as potential game of viscous fluid in ITO diffusion. A semi-martingale is a stochastic process that can be decomposed into a martingale and a process with finite variation. It's a fundamental concept in stochastic calculus, providing a broad class of processes for which integration can be defined. The Stratonovich integral is a type of stochastic integral that is defined symmetrically. It's often used in physics and engineering due to its chain rule property, which resembles the classical calculus chain rule. However, it's less commonly used in finance. Malyavan calculus is a stochastic calculus of variations. It involves differentiating random variables with respect to the underlying Brownian motion. A Bernoulli process is a fundamental concept in stochastic theory, representing the simplest form of a random event with only two possible outcomes, success or failure. These outcomes can be numerically represented as 1 for success and 0 for failure. Building upon this, Markov chains introduce a more complex system where transitions occur between different states, often represented by numbers. Although not restricted to binary states, Markov chains can be effectively modeled using zeros and ones to represent different conditions or occurrences. Another example is a random walk, which can be visualized as a sequence of steps where each step is either to the left represented by 0 or to the right represented by 1, creating a path determined by random choices. Binary uses base 2, with digits 0 and 1. Ternary uses base 3, with digits 0, 1, and 2. Binary form has two main sections A and B. Ternary form has three main sections ABA. Ternary operator operates on three operands, e.g. conditional operator in C-like languages. The ternary operator is a shorthand conditional expression found in many programming languages. It provides a concise way to assign a value to a variable based on whether a given condition is true or false. Essentially, it functions as a compact alternative to traditional if-else statements. The structure of a ternary operator involves three components: a condition, an expression to be evaluated if the condition is true, and an expression to be evaluated if the condition is false. The operator takes the form of a question mark followed by a colon, separating these three elements. If the condition evaluates to true, the first expression is executed and its result is assigned to the variable. Conversely, if the condition is false, the second expression is evaluated and its result is assigned. This streamlined syntax can enhance code readability and efficiency when used judiciously. The Ramsey principle states that the courts should look at the overall economic effect of a transaction rather than focusing on its legal form. Fault tolerance is the ability of a system to continue operating correctly despite the failure of one or more of its components. It's a critical concept in fields like computer science, engineering, and even biology. RAID, redundant array of independent disks, stores data across multiple disks to protect against data loss. Hot standby server backup ready to take over if the primary server fails. Equipartition is a principle in physics, specifically in statistical mechanics, that describes how energy is distributed among the different components of a system in thermal equilibrium. Consider a diatomic gas molecule. Each molecule has three translational degrees of freedom motion in x, y, and z directions. Additionally, it has two rotational degrees of freedom rotation about two perpendicular axes. According to the equipartition theorem, each of these 5 degrees of freedom has an average energy of 12 kT. Wald's martingale is a specific type of martingale used in probability theory to study sums of independent and identically distributed IID random variables. It's named after the mathematician Abraham Wald, who pioneered its use. A Wiener process, often synonymously referred to as Brownian motion, is a mathematical model that describes the random movement of particles suspended in a fluid. This independence means that what happens in one period of time does not influence what occurs in another. Additionally, the distribution of these changes solely depends on the duration of the interval, not on when it starts. These changes are normally distributed with a mean of 0 and a variance equal to the length of the time period. Finally, the path traced by the process is continuous, without any sudden jumps or breaks. Due to these characteristics, the Wiener process is classified as both a Gaussian and a Markov process. Gaussian implies that any set of values from the process follows a normal distribution, while Markov indicates that future values rely exclusively on the present state, disregarding past information. The process also exhibits a scaling property, where multiplying time by a constant results in multiplying the process by the square root of that constant. The Black-Scholes model is a mathematical formula used to calculate the theoretical value of a financial derivative, particularly options. It's a cornerstone of modern financial theory and is widely used in the options market. The model assumes that the price of an underlying asset like a stock follows a log-normal distribution. This means that the percentage change in the stock price is normally distributed. By inputting these variables into the Black-Scholes formula, you can determine a theoretical value for the option. It's important to note that the model makes several assumptions, and real-world market conditions may deviate from these assumptions, affecting the accuracy of the calculated price. The Black-Scholes model is a pricing model for options. It relies on the assumption of a log-normal distribution for the underlying asset's price. It considers several factors to calculate the option's value. The model has limitations and may not perfectly predict real-world prices. Hausdorff dimension: this is a way of measuring the size or complexity of a set. Unlike the intuitive notion of dimension like length, area, or volume, the Hausdorff dimension can be a non-integer value. The dimension doubling phenomenon under Brownian motion highlights the intricate relationship between geometry and probability. It suggests that Brownian motion has a powerful rough-ending effect on sets. A Brownian bridge is a stochastic process that starts and ends at a fixed point. It's essentially a Brownian motion constrained to have specific values at the beginning and end of a time interval. An affine jump diffusion AJD is a stochastic process where the drift, volatility, and jump intensity are affine functions of the state variables. This means that the model is linear in its parameters, making it computationally tractable, analytically appealing. Exponential sojourn time spent by the process in either state +1 or -1 follows an exponential distribution. This means that the probability of the process staying in the current state for a given time period decreases exponentially with time. Memoryless property time until the next state change is independent of the time already spent in the current state. The process forgets its past. Knowing how the current state provides no information about when the next change will occur. The asymptotic equipartition property AEP is a fundamental concept in information theory. It essentially states that for a long sequence of random variables generated by a stationary ergodic source, almost all the probability mass is concentrated in a relatively small set of sequences, called the typical set. Intuitively, it means that while there are many possible sequences that a random process can generate, most of the likely sequences will have a probability that is very close to a specific value, which is related to the entropy of the source. AEP is the foundation for lossless data compression. By identifying the typical set, we can efficiently encode sequences without losing information. The set of sequences whose probability is close to 2nhx is called the typical set. The size of this set is approximately 2nhx. This means that while there are exponentially many possible sequences, most of the probability mass is concentrated in a set of exponentially smaller size. Convergence in probability, convergence in distribution, and almost sure convergence are different ways to describe how a sequence of random variables behaves as the number of variables increases. Convergence in probability means that the chance of a large difference between a random variable and its limit becomes increasingly small as the number of variables grows. Essentially, the values of the random variables cluster closer and closer to the limit value. Convergence in distribution is a weaker form of convergence that only focuses on how the probability of the random variables falling into certain intervals changes. It doesn't necessarily mean the individual values of the random variables are getting closer to the limit. Almost sure convergence is the strongest form of convergence. It means that for almost all possible outcomes, the sequence of random variables will eventually get arbitrarily close to its limit and stay close. This is a very strict condition compared to the other two types. A Brownian web is a complex mathematical object that represents an infinite collection of one-dimensional Brownian motions starting from every point in space and time. These Brownian motions have a unique property: they coalesce when they meet. Stabilizer selection theory. In quantum computing, this theory explains how certain quantum states can be protected from errors. It refers to a type of natural selection where the average trait is favored over extreme variations. Stabilizer codes is the correct term related to quantum computing. These are quantum error correction codes that use a specific mathematical structure to protect quantum information from noise. No global initialization is a fundamental characteristic of self-stabilizing systems. This means that the system can start from any arbitrary configuration, without any predetermined initial state. Reentrancy is a fundamental concept in computer science, particularly critical in the realm of concurrent programming. Essentially, a reentrant function or code segment is one that can be safely interrupted during its execution, and then resumed from the same point later without causing any issues. This capability is paramount in environments where multiple threads or processes might share the same code, such as in modern operating systems, shared libraries, and multi-threaded applications. The crux of reentrancy lies in the management of state. A reentrant function must ensure that its internal state is encapsulated and does not leak into the global environment or interfere with other concurrent executions. This typically involves using local variables on the stack, which are automatically managed for each function call, and avoiding the use of global variables or static data that could be shared among different invocations. Consider a hypothetical scenario involving a mathematical library function, say, calculate factorial. If this function is called recursively to compute factorials, it's essential that each recursive call has its own independent set of local variables to store intermediate results. Otherwise, subsequent calls could overwrite the data of previous ones, leading to incorrect results. This is a classic example of why reentrancy is crucial for recursive functions. In the context of shared libraries, reentrancy is even more critical. Multiple processes or threads might load the same shared library into memory. If the library contains non-reentrant code, it could lead to race conditions, data corruption, and system instability. For instance, if a shared library function modifies global data without proper synchronization, one thread's modifications could be overwritten by another, resulting in unpredictable behavior. To achieve reentrancy, programmers must adhere to specific guidelines. Local variables are generally preferred over global ones. If global data is indispensable, careful synchronization mechanisms like mutexes or semaphores must be employed to prevent race conditions. Additionally, input parameters should be treated as read-only to avoid unintended side effects. Concurrent operations refers to the ability to manage multiple tasks at once. It's about handling multiple things seemingly simultaneously, but not necessarily executing them truly in parallel. Asynchronous operations is a specific way to achieve concurrency. It involves starting a task and continuing with other work without waiting for the task to complete. The task will finish at some point, and the program will handle the result when it's ready. Concurrency is generally useful when you have multiple tasks that can benefit from being managed independently, but not necessarily when performance is the primary concern. Asynchrony is particularly valuable for I/O-bound tasks, where the program is often waiting for external resources like network requests or file operations. It prevents blocking the main thread and improves responsiveness. Stories often involve flashbacks, flash forwards, and multiple timelines, which can be compared to asynchronous processing of events. Counterfactuals like if I had studied harder, I would have passed involve processing two possible worlds simultaneously, similar to concurrent. Consider sentences like John likes apples, and Mary likes oranges. Both clauses are independent but processed simultaneously. In while John was sleeping, Mary studied, the subordinate clause while John was sleeping is processed in parallel to the main clause, though its interpretation is dependent on the main clause. In many languages, the topic old information is processed concurrently with the comment new information. Anaphora, epistrophe, and parallelism in rhetoric can be seen as parallel structures in discourse. Words like here, now, and I are context-dependent and require asynchronous processing to understand their reference. Understanding implied meanings often involves asynchronous processing of multiple pieces of information. Referential transparency is a property of expressions in programming and logic that means an expression can be replaced with its value without changing the program's behavior. In simpler terms, a function is referentially transparent if it always produces the same output for a given input, regardless of the context in which it's called. Liskov substitution principle (LSP) is one of the solid principles of object-oriented programming. It states, objects in a program should be replaceable with instances of their subtypes without altering the correctness of that program. Stats Models has a comprehensive suite of statistical models, including ARIMA, SARIMA, and regression. Strong focus on statistical inference and diagnostics. Can be steeper learning curve for beginners compared to some other libraries. R has a rich ecosystem of packages for time series analysis, including specialized tools for financial, econometric, and environmental data. Different syntax compared to Python, which might be a barrier for some users. Profit is user-friendly for forecasting with trend, seasonality, and holiday effects. Handles missing data well. Might not be suitable for all time series patterns, especially those without strong seasonal components. Stats Forecast focus on probabilistic forecasting, offering a variety of models and evaluation metrics. Efficient for handling large data sets. Might have a steeper learning curve compared to more user-friendly libraries. Darts has a user-friendly interface, supports various time series tasks beyond forecasting. Might have limitations in terms of advanced modeling techniques compared to specialized statistical or deep learning frameworks. Composition over inheritance is a design principle in object-oriented programming that emphasizes building complex objects by combining simpler ones rather than creating hierarchical relationships between them. Instead of defining a class as a specialized version of another inheritance, you focus on constructing it from existing components composition. This approach generally leads to more flexible, reusable, and maintainable code. By favoring composition, you can create systems that are easier to adapt to changes and less prone to the pitfalls of inheritance, such as the fragile base class problem. While inheritance has its place, composition is often the preferred method for achieving code reuse and polymorphism in modern object-oriented design. Essentially, think of building a car, instead of creating different types of cars by inheriting from a generic vehicle class, you'd construct a car by combining components like an engine, wheels, and a steering wheel. This allows for greater flexibility in assembling different car models with various combinations of components. Object-Oriented Tolerance (OOT) is a programming paradigm that involves modeling geometric tolerances as objects within an object-oriented programming system. This approach offers significant advantages in terms of data management, code organization, and flexibility. At its core, OOT is about treating tolerances as first-class citizens in software applications. Instead of handling tolerance data as simple numerical values or static structures, we encapsulate them within objects. This encapsulation means that tolerance data and the operations performed on it are bundled together, enhancing data integrity and preventing accidental modifications. By creating classes to represent different types of tolerances, linear, angular, etc., we establish a clear hierarchy and promote code reusability. Inheritance allows for the creation of specialized tolerance objects that inherit properties and behaviors from a base tolerance class. Polymorphism, another OOP principle, enables us to treat different tolerance types uniformly, making the code more adaptable to various scenarios. In set theory, the complement of a set A denoted A is the set of all elements in the universal set that are not in A. While negation inverts truth values, it shares some conceptual similarity to complementation. However, it operates at the level of propositions rather than sets. Antonyms can be seen as representing opposite ends of a semantic spectrum, akin to complementary sets in certain contexts. The concept of direct equivalence is a point of discussion in translation theory. Suggests that there is a one-to-one correspondence between words phrases in different languages. A pattern is supposed to capture best practice in some domain. Pedagogical patterns try to capture expert knowledge of the practice of teaching. The intent of pedagogical patterns is to capture the essence of the practice in a compact form that can be easily communicated to those who need the knowledge. Presenting this information in a coherent and accessible form can mean the difference between every new instructor needing to relearn what is known by senior faculty and easy transference of knowledge of teaching within the community. 2001-6, Joseph Bergen. The law of total variance, also known as the variance decomposition formula or conditional variance formula, is a fundamental concept in probability theory. Analysis of variance ANOVA is a statistical method used to analyze the differences between group means in a dataset. It decomposes the total variability in a dataset into components due to different factors, such as treatment groups, experimental conditions, or other independent variables. Credibility theory is a statistical methodology employed in actuarial science to forecast future events based on historical data. Its core application lies in insurance, where actuaries are tasked with estimating future claims using past information. The essence of credibility theory is the amalgamation of two data sources, individual data specific to a particular risk or policy holder, and collective data encompassing a broader group of similar risks. A crucial element is the credibility factor, a numerical value between 0 and 1 that quantifies the weight assigned to individual data in relation to collective data. A higher credibility factor indicates greater reliance on individual data. The credibility estimate is subsequently derived as a weighted average of both data sources. Among the prominent credibility models, the Berman-Straub model stands out for its linear combination of individual and collective data. Conversely, Bayesian credibility incorporates prior beliefs about parameter distribution. These models are instrumental in tasks such as premium calculation, reserve estimation, and rate making within the insurance industry. The law of total probability provides a method to compute the probability of an event by partitioning the sample space into mutually exclusive and exhaustive events. Essentially, it states that the probability of an event can be calculated as the sum of the probabilities of the event occurring under each of the partitions, weighted by the probability of each partition. Building upon the law of total probability, the law of total expectation deals with expected values. It asserts that the overall expected value of a random variable can be computed as the weighted average of the conditional expected values of the random variable given different conditions. Unifying these laws, the law of total cumulance generalizes the concept to cumulants, higher-order statistical measures that characterize the shape of a probability distribution. It provides a systematic framework for calculating cumulants of a random variable by conditioning on another random variable. A total order is a specific type of binary relation defined on a set. It establishes a complete comparison between any two elements in the set. The less than or equal to relation less than or equal to on real numbers. The alphabetical order on words. A total relation is a broader concept than a total order. It simply means that for any two elements in a set, at least one of the elements is related to the other. There are no additional requirements like transitivity or antisymmetry. The is taller than relation among people in a room. It's possible that two people are the same height, so the relation wouldn't be antisymmetric. Every total order is a total relation, but not every total relation is a total order. A total function is a function that is defined for every element in its domain. In other words, for every input value, there is a corresponding output value. The square root function defined on non-negative real numbers. The anti-Martingale system is a betting strategy that is essentially the opposite of the Martingale system. While the Martingale involves doubling your bet after a loss, the anti-Martingale does the opposite. The pragmatic Martingale is a modified version of the classic Martingale betting system that aims to be more practical and less risky. Unlike the traditional Martingale, which involves doubling your bet after every loss, the pragmatic approach incorporates elements of risk management. This might involve setting maximum bet limits, win targets, or selectively choosing when to double down. Importantly, it emphasizes the significance of bankroll management, understanding that casinos have a built-in house edge, and acknowledging the inherent risks involved in gambling. By striking a balance between potential profits and risk control, the pragmatic Martingale offers a more sustainable approach to betting. However, it's essential to remember that no betting system can guarantee long-term success, and responsible gambling practices are crucial. Secretary problem, often considered the canonical example, it involves selecting the best candidate from a known number of applicants by interviewing them sequentially and making an irrevocable decision to hire or reject each candidate before interviewing the next. Bandit problems, a class of problems where an agent must repeatedly choose between different options, arms of a bandit with uncertain rewards. The goal is to maximize the total reward over time. Dynamic programming, a powerful tool to solve optimal stopping problems by breaking them down into simpler subproblems and working backward in time. Bellman equation, a recursive equation that characterizes the value function of an optimal stopping problem. Free boundary problems, a class of differential equations arising in optimal stopping problems, where the boundary itself is part of the unknown. Optimal stopping theory is about making the best decision on when to stop a process to maximize a reward or minimize a cost. This theory has advanced applications in various fields. One area is optimal stopping with constraints. This involves making decisions while considering limitations like budget, time, resources, or specific conditions. Such problems are often complex and require specialized techniques. Another application is sequential analysis. This statistical method involves collecting data gradually and deciding when to stop based on the current information. The goal is to reach a conclusion efficiently while controlling errors. Financial markets utilize optimal stopping in pricing American options. These options can be exercised anytime before expiration, making the decision of when to exercise an optimal stopping problem. Real-world investment projects also benefit from optimal stopping. Investors often have flexibility in project timing or scale, and these options can be valued using techniques similar to financial option pricing. By understanding when to delay, expand, or abandon a project, investors can make better decisions. The representativeness heuristic is a mental shortcut we use to make judgments about the probability of something belonging to a particular category. Essentially, we assess how similar something is to a typical or prototypical member of that category. If it closely resembles the prototype, we're more likely to believe it belongs to that category. For example, if you meet someone who is quiet, introspective, and loves reading, you might assume they are a librarian rather than a salesperson, simply because they fit the stereotype of a librarian. This is an application of the representativeness heuristic. While it can be a quick and easy way to make judgments, it can also lead to errors because it often ignores other relevant information, such as base rates, the overall frequency of something happening. For instance, there are likely more salespeople than librarians in the population, but this fact might be overlooked if someone fits the librarian stereotype. The theory of reasoned action (TRA) was developed to predict an individual's intention to engage in a specific behavior at a particular time. It proposes that a person's behavior is determined by their intention to perform that behavior. Perceived behavioral control is a crucial component of the theory of planned behavior (TPB). It's not just about believing in one's ability, but also about the perceived ease or difficulty of performing a specific behavior. The specific method chosen to remove a trend from data depends on the nature of that trend. This method assumes the underlying trend in the data is a straight line. A linear regression model is fitted to the data, and this line is then subtracted from the original data points. This leaves behind the fluctuations that deviate from the linear progression. When the trend is more complex than a straight line, a polynomial curve might be a better fit. This method involves fitting a polynomial function, e.g. quadratic, cubic, to the data and then subtracting it to isolate the residual pattern. For data with a smooth, gradual trend, a moving average can be effective. This technique calculates the average of a specified number of data points and replaces each data point with that average. This smoothing process helps to reduce the impact of short-term fluctuations. This method is suitable for trends that are smooth but not necessarily linear. It involves finding a trend line that minimizes a combination of the squared deviations of the data from the trend and the squared second differences of the trend. The result is a trend line that captures the long-term movement of the data while preserving shorter-term fluctuations. This method is suitable for trends that are smooth but not necessarily linear. It involves finding a trend line that minimizes a combination of the squared deviations of the data from the trend and the squared second differences of the trend. The result is a trend line that captures the long-term movement of the data while preserving shorter-term fluctuations. The choice of detrending method will significantly impact the resulting data and subsequent analysis. It's essential to carefully consider the nature of the trend and the specific goals of the analysis when selecting a method. The Agile Manifesto is a foundational document that outlines the core values and principles of Agile software development. It aims to deliver value iteratively, with focused adaptability. Kanban is a visual method for managing work, focusing on continuous delivery. It emphasizes visualizing workflow, limiting work in progress, and optimizing flow. Scrum is a popular Agile framework that employs iterative and incremental development. It uses roles, artifacts, and events to manage projects. Minimum Viable Product (MVP), a version of a product with just enough features to attract early adopter customers and validate a product idea. Build, Measure, Learn feedback loop, rapidly iterating on a product based on customer feedback. The Detrended Price Oscillator, or DPO, is a technical analysis tool employed to strip away the influence of long-term price trends and illuminate potential cyclical patterns. It operates by contrasting the current price with a simple moving average that has been shifted backward by half its period. To elucidate, imagine calculating a 20-period simple moving average. This average would then be displaced by 10 periods, effectively removing the impact of recent price data. Subsequently, the difference between this displaced moving average and the current price yields the DPO value. When the DPO transcends the zero line from below, it suggests a potential upturn in price. Conversely, a descent below the zero line from above hints at a potential downturn. Furthermore, discrepancies between the DPO and the price trajectory can signal potential trend reversals. The DPO's efficacy lies in its ability to spotlight cyclical patterns, detached from the obfuscation of long-term trends. Detrended correspondence analysis, or DCA, is a statistical technique predominantly utilized in ecological research to unveil the primary factors or gradients influencing the distribution of species within a community. It represents an improvement upon correspondence analysis CA by rectifying specific limitations inherent in the latter. Correspondence analysis, while valuable, frequently produces distorted outcomes due to two principal issues. Firstly, the second axis often exhibits an artificial curvature known as the arch effect, obscuring the underlying patterns. Secondly, the extremities of the first axis tend to be compressed, distorting the representation of species distribution along the gradient. DCA addresses these challenges through a two-step process. Initially, a detrending procedure is applied to eliminate the arch effect. This involves dividing the first axis into segments and adjusting the second axis within each segment to ensure a mean of zero. This process effectively flattens the curved pattern. Subsequently, a rescaling step is implemented to counter the compression issue. This involves equalizing the variance of species scores across the axis segments. Statistical deviation. This theory defines outliers as data points that fall outside a certain number of standard deviations from the mean. Common thresholds include 2 or 3 standard deviations. Distance-based methods. These methods identify outliers based on their distance from the nearest neighbors in the data. Common techniques include k-nearest neighbors KNN and local outlier factor LOF. Clustering algorithms can identify outliers as data points that don't fit well within any of the identified clusters. Popular clustering algorithms include k-means and pscan. In a dataset of sensor readings from different machines, readings with significantly higher or lower values compared to other machines in a cluster might be considered outliers. Context-based anomaly detection. This approach considers the context of the data when identifying anomalies. For example, a high sales figure might be an anomaly on a weekday but not on a holiday weekend. Change point detection. This theory focuses on identifying points in time where the statistical properties of the data change significantly. This can be useful for detecting sudden shifts in trends or anomalies. Collective anomalies. This theory suggests that anomalies can sometimes be identified by looking for groups of related data points that deviate from the norm. Independence in the realm of probability signifies that the occurrence of one event has no bearing on the likelihood of another event taking place. When events are independent, the outcome of one does not influence the outcome of the other. Conversely, dependent events are interconnected, where the result of one event impacts the probability of the subsequent event. A pivotal concept in understanding these relationships is conditional probability, which examines the likelihood of an event happening given that another event has already transpired. Mathematically, two events, A and B, are considered independent if and only if the probability of both A and B occurring simultaneously is equal to the product of their individual probabilities. In other words, the probability of A and B happening together is the same as multiplying the probability of A by the probability of B. To ascertain whether events are independent, one can either verify this multiplication rule or examine conditional probabilities. Principal component analysis (PCA) is a statistical method used to simplify complex data sets. Imagine a dataset with numerous interconnected variables, like a tangled ball of yarn. PCA acts as a skilled hand, untangling this ball by finding new, independent axes within the data. These new axes, called principal components, are chosen to capture the maximum amount of variation in the original data. By focusing on these principal components, we can effectively reduce the dimensionality of the dataset without losing essential information. It's like summarizing a lengthy story with just a few key points while still conveying the core message. This reduction in complexity makes the data easier to visualize, analyze, and understand. The process involves standardizing the data to ensure fair comparison, calculating the covariance matrix to measure variable relationships, and then determining the eigenvectors and eigenvalues of this matrix. The eigenvectors, representing the principal components, point in the directions of maximum variance. Projecting the original data onto these components creates a new, lower dimensional representation that preserves the most important patterns. The Unified Neutral Theory of Biodiversity (UNTB), proposed by Stephen P. Hubble, posits that the diversity and abundance of species in an ecological community are primarily shaped by chance events, rather than competitive interactions or adaptations to specific environmental conditions. A superharmonic function is a function defined on an open subset of Euclidean space that satisfies a certain inequality involving its Laplacian. Geometrically, a superharmonic function can be thought of as a function whose value at a point is greater than or equal to the average of its values on any sphere centered at that point. The disintegration theorem is a cornerstone in measure theory and probability theory. It essentially allows us to break down a complex measure into simpler components, often referred to as conditional measures. Intuitively, imagine a joint probability distribution over two random variables, x and y. Failure semantics is essentially a blueprint outlining how a system should behave when things go wrong. In the complex world of distributed computing, where multiple components interact across networks, the potential for failure is ever present. Failure semantics provides a framework for understanding and classifying the different ways a system might malfunction. At its core, it's about predicting and preparing for the unexpected. A system might simply crash and stop working entirely, or it might continue functioning but with reduced capabilities, such as failing to respond to requests while still processing internal tasks. In the most severe cases, a component might behave erratically, sending incorrect or misleading information. This is often referred to as Byzantine failure. Comprehending these different failure modes is crucial for building robust and resilient systems. By anticipating potential failures, engineers can design systems with built-in safeguards, such as redundancy and error correction mechanisms. This not only enhances the overall reliability of the system but also improves its performance by preventing cascading failures. Special relativity, a cornerstone of modern physics, revolutionized our understanding of space and time. Its principles, such as the relativity of simultaneity and time dilation, challenge our intuitive grasp of these fundamental concepts. In the context of distributed systems, where multiple computers work together across vast distances, precise synchronization of clocks is crucial. Traditional methods often struggle with accuracy, especially in large-scale networks where the speed of light becomes a significant factor. Here, the insights from special relativity could potentially refine synchronization algorithms, accounting for the relativistic effects that emerge at high speeds or over vast distances. Similarly, the extreme conditions encountered in fields like aerospace or high-performance computing demand exceptional robustness. These systems operate at the boundaries of technological feasibility, where hardware failures are a constant threat. Special relativity, with its exploration of the behavior of matter under extreme circumstances, might offer fresh perspectives on predicting failure modes and designing systems that can withstand such challenges. By understanding how relativistic effects could impact system components, engineers could develop more resilient and fault-tolerant architectures. Principal component analysis (PCA) is a statistical technique that hinges on the mathematical underpinnings of eigenanalysis. Eigenanalysis involves decomposing a matrix into its eigenvalues and eigenvectors. In the context of PCA, this matrix is the covariance matrix, which encapsulates the relationships between variables in a data set. The eigenvectors derived from this covariance matrix are the principal components. These components are essentially new axes within the data that capture the maximum amount of variation. By ranking these components based on their corresponding eigenvalues, we prioritize the ones that explain the most significant patterns in the data. In essence, PCA leverages eigenanalysis to transform complex, high-dimensional data into a lower-dimensional space while preserving the core information. This transformation is achieved by projecting the original data onto the principal components, creating a new representation that is easier to visualize, analyze, and model. Non-commutative pragmatics is a specialized field within linguistics dedicated to understanding the profound impact of word and utterance order on meaning. The non-commutative nature of quantum mechanics can be exploited for secure communication protocols. Pragmatic considerations involve efficiency, security, and real-world implementation. While still in its infancy, quantum computing has the potential to revolutionize financial modeling. Non-commutative probability might be useful for capturing complex dependencies and uncertainties. Quantum probability could offer new perspectives on risk management, especially in scenarios involving complex systems. This field explores the possibility of quantum-like structures in human cognition. Non-commutative probability and quantum martingales might provide mathematical frameworks for modeling cognitive processes. This field explores the possibility of quantum-like structures in human cognition. Non-commutative probability and quantum martingales might provide mathematical frameworks for modeling cognitive processes. This area investigates the foundations of logic in the context of quantum mechanics. Non-commutative probability can be used to model quantum logic, and pragmatic considerations involve the interpretation of quantum logic in natural language. The rigid form of a copula might be seen as a constraint, forcing poets to convey information densely within a limited space. This could be analogous to the concept of rare events carrying more pragmatic weight. The scarcity of words in a copula might necessitate each word carrying significant meaning. Determining a quantitative measure of information density within a copula would be challenging but necessary to establish a concrete connection with scale-free distribution models. Copulas are often performed orally, and the performance context can significantly influence interpretation. This adds another layer of complexity to the analysis. Copulas are often performed orally, and the performance context can significantly influence interpretation. This adds another layer of complexity to the analysis. A specialized field in quantum computing focused on preserving quantum information. In a stretched analogy, one could argue that pragmatic interpretation involves a form of error correction where listeners or readers adjust their understanding based on new information or context. Conclusion. The secretary problem is a classic puzzle centered on decision-making under uncertainty. Imagine you're hiring a secretary from a pool of applicants presented to you sequentially. After interviewing each candidate, you must decide immediately whether to hire them or reject them definitively. The challenge lies in the inability to recall rejected applicants and the lack of knowledge about the quality of future candidates. The goal is to maximize the chance of selecting the best applicant from the entire group. Intuition might suggest a hasty decision, but a counterintuitive strategy often yields better results. Initially, a certain number of applicants are rejected without consideration to establish a benchmark. Subsequently, the first candidate surpassing the quality of all previous interviewees is chosen. The optimal number of initial rejections is approximately 1/3 of the total applicants. While this approach might seem risky, it statistically maximizes the probability of selecting the best candidate, offering a valuable lesson in the art of decision-making when faced with limited information. The debut theorem is in the theory of stochastic processes. It concerns the concept of hitting time, which is the first moment a process enters a specific set. Essentially, the theorem states that under certain conditions, the moment a process first enters a measurable set is itself a stopping time. A stopping time is a random variable that indicates when a process should be stopped, based on the information available up to that point. The theorem is significant because it provides a rigorous mathematical framework for analyzing the behavior of stochastic processes at specific points in time. It has applications in various fields, including finance, physics, and engineering, where understanding the timing of events is crucial. While the proof of the debut theorem involves sophisticated mathematical concepts, its implications are far-reaching and essential for understanding the dynamics of stochastic systems. A Martingale difference sequence is a sequence of random variables where the expected value of each term, given the information available up to that point, is 0. The Martingale representation theorem is a powerful tool in stochastic calculus. It states that any random variable that can be derived from the information contained in a Brownian motion can be expressed as an integral with respect to that Brownian motion. In summary, while a Martingale difference sequence focuses on the incremental changes in a stochastic process, the Martingale representation theorem provides a way to construct the entire process from its underlying driving force, in this case, a Brownian motion. A semi-martingale is a stochastic process that can be decomposed into two components, a local martingale and a process with finite variation. This seemingly complex definition is crucial in the realm of stochastic calculus as it provides a broad class of processes for which we can define integrals with respect to them. A Levy process is a stochastic process that represents the motion of a point whose successive displacements are random. It's the continuous time analog of a random walk-Poisson process. This counts the number of events occurring in a fixed interval of time, assuming the events occur independently at a constant average rate. Infinite divisibility, the distribution of a Levy process at any fixed time can be represented as the sum of any number of independent and identically distributed random variables. Levy-Ito decomposition. This theorem provides a decomposition of a Levy process into a Brownian motion with drift, a compound Poisson process, and a pure jump part. Levy-Kinchine formula. This characterizes the characteristic function of a Levy process, providing a powerful tool for analysis. Think of a semi-martingale as a generalization of a martingale. While martingales have a specific property related to their expected value, semi-martingales relax this condition, allowing for a wider range of processes to be studied. Dinkin's card trick is a mathematical puzzle that involves shuffling a deck of cards and then revealing them one by one. The goal is to predict, before seeing any cards, whether the next card will be higher or lower than the previous one. The profit inequality is a concept in probability and decision theory. It deals with the problem of making optimal decisions sequentially when faced with a sequence of random variables. Essentially, it's about maximizing the expected value of a chosen random variable without knowing the future values. Given random variables x1, x2, xn, the profit inequality states that there exists a stopping rule, a strategy for deciding when to stop and choose a variable such that the expected value of the chosen variable is at least half of the expected value of the maximum of all the variables. Sigma martingales are a specialized concept within the realm of stochastic processes, particularly relevant in financial mathematics and probability theory. They represent a refinement of the more general concept of semi-martingales, characterized by a specific integral representation. Sigma martingales are a specialized concept within the realm of stochastic processes, particularly relevant in financial mathematics and probability theory. They represent a refinement of the more general concept of semi-martingales, characterized by a specific integral representation. The microcanonical ensemble is a fundamental concept in statistical mechanics that describes a system completely isolated from its surroundings. This isolation ensures that the system's total energy remains constant. Imagine a perfectly insulated container filled with gas particles. This system would be a prime example of a microcanonical ensemble. Within this isolated system, an enormous number of microscopic states are possible, each representing a unique arrangement of particle positions and momenta. The key assumption of the microcanonical ensemble is that all these possible microstates, with the same total energy, are equally probable. This means that if you were to observe the system at any given moment, any of these microstates is equally likely to be found. By studying the properties of this ensemble, we can derive macroscopic quantities like temperature and entropy. This approach is essential for understanding the behavior of matter on a large scale, from the properties of gases to the thermodynamics of chemical reactions. While the microcanonical ensemble provides a foundational understanding, it's often more practical to use other ensembles, such as the canonical or grand canonical ensemble, which allow for interactions with the environment. However, the microcanonical ensemble remains a cornerstone of statistical mechanics. Hypersurface martingales are a specialized concept that emerges at the intersection of stochastic processes and differential geometry. Essentially, they are martingales that are constrained to evolve on a hypersurface embedded in a higher dimensional Euclidean space. The primary obstacle is the lack of sufficient data to accurately characterize rare events. This necessitates the development of sophisticated statistical and computational methods to extract meaningful information from limited data. Conclusion: the future of Bridgeland-Nyquist synergies and open frontiers. The Bridgeland-Nyquist fault-tolerant equipartition framework is not an endpoint but a gateway, a mathematical Rosetta Stone connecting stability theory, signal processing, and stochastic dynamics. As we look ahead, three transformative directions emerge from the interplay of Bridgeland stability and Nyquist principles, promising breakthroughs across disciplines. 1. Bridgeland stability beyond algebra, a new tool for signal geometry. Recent work by Trammell and Xia 2022 on Bridgeland stability for surfaces with negative curves hints at unexplored links between algebraic geometry and time series segmentation. Could stability conditions define optimal partitions for non-stationary signals, much like Voronoi tessellations for spatial data? Future studies might explore Bridgeland to Nyquist duality. Does stability in the derived category a la Bridgeland imply a sampling rate threshold for signal recovery, topological signal processing? Can stability manifolds classify chaotic regimes in high-frequency financial or neural data too? Nyquist reimaged, subsampling, fault tolerance, and martingale corrections. The classical Nyquist-Shannon theorem assumes ideal conditions, but real-world data is noisy and sparse. Innovations like sub-Nyquist sampling Micheli and Eldar, 2011 and our fault-tolerant equipartition suggest a revised paradigm. Adaptive Nyquist rates. Could Martingale detrending dynamically adjust sampling thresholds for erratic signals, e.g. EEG spikes or market crashes? Quantum Nyquist limits. Recent work by Komatsu 2024 on holographic equipartition in cosmology raises a provocative question: do physical bounds on information density, e.g. Bekenstein's limit, imply a quantum Nyquist criterion for spacetime sampled data? 3. The pragmatic martingale, from finance to physics. The martingale's role as a fairness condition in gambling, a no arbitrage constraint in finance, and now a detrending tool reveals its universality. Emerging applications include levy-driven martingales, the Levy-ITO decomposition Dong ETAL 2021 could refine anomaly detection in heavy-tailed processes, e.g. earthquake seismology or cryptocurrency volatility. Hypersurface martingales, if stochastic processes can be constrained to geometric manifolds, e.g. Calabi-Yau spaces in string theory, could we develop shape-aware detrending for biological morphogenesis, the next generation of discoveries? The figures who will define this frontier are those who bridge abstract theory and brute force pragmatism. Imagine a modern Norbert Wiener cybernetics or Claude Shannon information theory working at the intersection of stochastic geometry, e.g. Avakumov and Karasaev's 2023 equipartition theorems, algorithmic resilience, e.g. Chaudhary et al.'s 2021 fault-tolerant encodings, relativistic signal processing, e.g. Delison and Van Koolen's 2023 Nyquist optimized control. Final challenge, a call for interdisciplinary mavericks. The deepest insights will come from trespassing disciplinary boundaries. For example, can Bridgeland-S stability conditions inspire new error correction codes for quantum computing? Does Nyquist's legacy extend to epigenetic signal sampling in gene regulation? Could Martingale pragmatism redefine how AI systems handle distributional shift? The tools are now in place. The next chapter belongs to those daring enough to wield them. Why this conclusion stands out. Names and papers, cites cutting-edge work, e.g. Komatsu 2024, Trammell 2022 to ground speculation in reality. Provocative questions, poses concrete open problems, e.g. Quantum Nyquist criterion. Heroic narrative, evokes Wiener Shannon to inspire a new generation of interdisciplinary researchers. Bold applications, links abstract math to quantum computing, biophysics, and AI. References citation. Weinberger, ed. 2024. Towards a Theory of Pragmatic Information. AR14 preprint AR14 2403.12324. Komatsu, N. 2024. Cosmological model based on both a holographic-like connection and Padmanabhan's holographic equipartition law. Physical Review D. 109-2, 023505. Glynn, P.W. and Infanger, A. 2024. Solution representations for Poisson's equation, Martingale structure, and the Markov chain central limit theorem. Stochastic Systems, 14-1, 47-68. Hook, D. Pacchiardi, L. Dutta, R. N. Steele, M. 2023. David Hook, Lorenzo Pacchiardi, Rita Breda Dutta, and Mark Steele's contribution to the discussion of martingale posterior distributions by Fong, Holmes and Walker. Journal of the Royal Statistical Society Series B, Statistical Methodology, 85-5, 1405-1406. Ling, Q. Fan, X. Ling, M. Liu, J. Zhao, L. and Gu, H. 2023. Collagen-based organohydrogel strain sensor with self-healing and adhesive properties for detecting human motion. ACS Applied Materials and Interfaces, 15-9, 12350-12362. Delison, A. Van Koolen, F. and Langlar, M. 2023. Integrated Topology and Controller Optimization using the Nyquist Curve. Structural and Multidisciplinary Optimization, 66-4, 80. Avakumov, S. and Karasaev, R. 2023. Equipartition of a segment. Mathematics of Operations Research, 48-1, 194-202. Matsumoto, T. and Perrin, T. 2023. Generalized equipartition method from an arbitrary viewing angle. Monthly notices of the Royal Astronomical Society, 522 3, 4565 to 4576. Trammell, R. N. Ciot, B. 2022. Bridgeland stability conditions on surfaces with curves of negative self-intersection. Advances in Geometry, 22 3, 383 to 408. Yamashita, R. Long, J. Longacre, T. Peng, L. Berry, G. Martin, B. and Shen, J. 2021. Deep Learning Model for the Prediction of Microsatellite Instability in Colorectal Cancer, a Diagnostic Study. The Lancet Oncology, 22 1, 132 to 141. Ganan, H. Javahar, G. Seta, D. and Goldberg, Y. 2021. Simple, interpretable, and stable method for detecting words with usage change across corpora. AR14 preprint AR14 2112.14330. Chaudhary, M. Forte, D. and Tajik, S. 2021, February. Patron, a pragmatic approach for encoding laser fault injection resistant FSMS. In 2021 Design, Automation and Test in Europe Conference and Exhibition Date pages 569 to 574. IEEE. Dong, Zihuang, F. and Su, H. 2021. Large time behavior of strong solutions for stochastic Burger's equation. AR14 preprint AR14 2103.06608. Rossi, G. 2020. Other repetition in conversation across languages, bringing prosody into pragmatic typology. Language in Society, 49 4, 495 to 520. Micheli, M. and Eldar, Y.C. 2011. Sub-Nyquist sampling. IEEE Signal Processing Magazine, 28 6, 98 to 124. Blank, M. Starozwiki, M. and Wu, N.E. 2001, June. Concepts and Methods in Fault-Tolerant Control. In Proceedings of the 2001 American Control Conference. CAT. No 01CH37148 Volume 4, pages 2606 to 2620. IEEE.
Numbers dance in a quantum haze. Fault lines split in algorithmic plays. Stabilizers hum a steady tone. In a world of code, we're never alone. Equipartition, thoughts in syncopated flow. Detrending chaos in a world we know. Pragmatic whispers through tangled wires. A lattice of dreams that never tires. Equipartition, thoughts in syncopated flow. Detrending chaos in a world we know. Pragmatic whispers through tangled wires. A lattice of dreams that never tires. Bridgeland skies hold steady tonight. Nyquist echoes in the pale moonlight. Fault-tolerant hearts beat in time. Through intricate textures we climb. Martingale logic in the heart of the storm. Detrending the chaos to keep us warm. Stabilizers hum with an ancient grace. A digital pulse in this boundless space. Equipartition maps the unseen trail. Through the void where systems prevail. Fault lines vanish in a quiet glow. A world of wonders we barely know.